is Dr. Anthony Filippi, faculty member in the Department of Geography here at Texas A&M University in College Station, Texas. And here I will be discussing geometric correction or geometric rectification of remote sensing imagery with a focus on multispectral passive remote sensing imagery. It's often necessary to perform digital image pre-processing of remotely sensed image data in order to remove or minimize geometric distortions that are inherent within the image in order for the picture elements or pixels within the image to be placed into their proper planimetric XY map locations. And if we're able to do that, we could then analyze jointly the remotely sensed image data that we have geometrically corrected and or the remote sensing derived data products from that remotely sensed image data set with other types of spatial data layers that may be resident within a geographic information system. All of the various data layers, the remote sensing images, derived products, and other GIS data layers just need to be spatially co-registered with one another in the same map projection and datum, etc. And if we have all that, we could then perform GIS-based modeling or spatial analyses. We can make decisions within a spatial decision support system framework, etc. But we do need to have geometrically corrected images. And if we have that, then we can perform extraction of accurate measurements of distances, areas of various polygons that we may be interested in describing, and we can also make accurate direction or bearing measurements. Geometric errors that exist within a remotely sensed image dataset can be either internal or external in origin, and it's important to understand the nature and the source of these errors, as well as whether or not they are systematic or predictable, or non-systematic or random in nature. And in general, if we have a systematic or predictable type of an error, that's usually going to be more easily correctable than a non-systematic or a random error. Now, I will just very briefly discuss in an overview format the nature of internal and external geometric errors, but I won't go into a great amount of detail about this. Here in this lecture, I'm going to be focusing on how do we actually perform the geometric correction, but I'll just briefly discuss the nature of internal and external geometric errors. I'll first briefly discuss internal geometric errors, and these types of errors are introduced by the remote sensing system itself, or it could be in combination with the Earth's rotation or the Earth's curvature characteristics. And often these types of errors are systematic or predictable in nature, and thus they may be identified and corrected for using pre-launch or in-flight platform ephemeris data. And that's just referring to the geometric characteristics of both the sensor system as well as the Earth at the time of data acquisition. And the types of errors that could be corrected for in this manner are as follows. So that can include the skew that is caused by Earth rotation effects. And often if you receive data from the data vendor, typically those types of errors, which again are highly predictable, are typically already going to be corrected for. Scanning system induced variation in ground resolution size. And here when I say scanning system, I'm referring to a whisk broom type scanner. Also scanning system one-dimensional relief displacement, as well as scanning system tangential scale distortion. I won't be discussing all of these various types of errors in detail, but again, we have a brief list here, and I'll say a little bit more about that in the next slide. One of the multispectral whisk broom scanning system induced errors that I'll just briefly mention here is the variation in ground resolution cell size. And what that's referring to is the fact that if we have a whisk broom scanner, we can have variation in the pixel size for pixels and the associated data that are collected at nadir versus from an off-nadir viewing perspective. And so if we have an orbital multispectral scanning system, remember with a whisk broom scanner, we have a mirror that's oscillating and scanning back and forth at a rapid rate over this arc, this field of view. If we have a satellite or orbital-based multispectral scanning system, it's really just going to be scanning through a few degrees off nadir as it is collecting data from hundreds of kilometers above the Earth's surface. And the net effect of this is that it's going to minimize the amount of distortion then that's going to be introduced by the scanning system in this manner. Because remember, typically for an Earth resource or environmental type of satellite, these are usually going to be orbiting the Earth on the order of about 700 to 900 kilometers above the Earth's surface. So that's a significant distance. In contrast, if we have a suborbital or airborne-based platform that is carrying a multispectral whisk broom scanner, it may just be operating tens of kilometers above ground level, for example, and it may be scanning over a field of view of, say, maybe 70 degrees. And if we have a scenario, a geometric construction of that nature, it's going to introduce numerous types of geometric distortions that could potentially be difficult to correct. Regarding external geometric errors, these are errors that are usually introduced by phenomena that vary in nature through both space and time. And the most important external types of variables that can often lead to geometric distortions in remote sensing image data are often going to be associated with random movements by aircraft or spacecraft at the time of the image acquisition. This includes changes in the altitude of the sensor, throughout a given flight line, and or attitude changes, and that includes roll, pitch, and yaw effects. I will say here that we would typically see these types of external geometric errors most closely associated with aircraft or suborbital based remote sensing. Just because those types of sensor platforms, aircraft platforms, are going to be influenced by wind effects, turbulence effects, etc. So we're going to see much higher magnitude external errors typically with aircraft-based remote sensing than with spacecraft-based remote sensing. So this figure summarizes geometric modifications of remotely sensed image data that are caused by changes in platform, both altitude and attitude. And in this figure we have 4 rows of images, and these are broken up into subfigure A, and then we have the next 3 rows that are referring to subfigure B. Subfigure A is referring to an illustration of what happens when we have a change in platform altitude, whether it be a aircraft or spacecraft, and then the next 3 rows are referring to an illustration of what happens when we have different types of changes in the attitude of our aircraft. So if we have roll effects, that's the first row of subfigure B. What happens when we have pitch effects? That's the second row of subfigure B. And the last row of subfigure B is an illustration of what happens when we have yaw effects. And I'll briefly discuss each one of these. So in subfigure A, note that we can have geometric modification of our images that could be introduced by changes in the altitude of our aircraft or spacecraft platform above ground level when we are in the process of collecting our image data. So if we increase our altitude, that's going to result in smaller scale or less detailed images, whereas if we are decreasing the altitude of our platform, that's going to result in larger scale images. So that's what the effect is of changes in altitude. In terms of changes in attitude, let's first consider the roll effects. Okay, so again, we can have geometric modifications or distortions that are introduced to a remotely sensed image if we have changes in terms of roll, pitch, and yaw. So in terms of roll, here we have an aircraft that is flying in an X direction, and roll occurs when our aircraft or spacecraft fuselage is maintaining directional stability along its flight line, but the wings move up and down. So here we have rotation about the X axis angle, omega. Okay. We have changes in pitch that occurs when the wings are stable, but the fuselage, nose, or tail moves up and down. And this is the scenario that's the second row there of subfigure B, the pitch effects. So here we have rotation about the y-axis angle in this particular case, if the nose is moving up or down. So we have rotation there about the y-axis angle phi, or phi. And then the final situation, the yaw effects, that bottom row of the figure. We have yaw occurring when the wings remain parallel, but the fuselage is forced by wind to be oriented at some angle to the left or right of the intended line of flight. So we have then in that case rotation about the z-axis angle kappa. Okay, so thus we have the plane uh, that is flying straight, but all the remote sensing image data are going to be displaced by kappa. And keep in mind that remote sensing images are often going to be distorted due to some combination, right, of changes in altitude and attitude, roll, pitch, and yaw. So often yes, in some cases it may just be one of these errors that we're seeing, but often throughout a flight line we're going to see some combination of potentially all of these types of errors. So these various types of geometric distortions due to sensor system attitude, the roll, pitch, and yaw effects, as well as attitude changes, can be corrected if we utilize ground control points or GCPs, as well as the appropriate mathematical models. So first, let's start out with defining what a ground control point is, or a GCP, and that is simply just a location on the Earth's surface. Usually it's something that we're going to be able to easily identify, something like a road intersection or maybe the corner of a building, something like that. Often they're going to be associated with cultural features that are imposed on the landscape. But we want to be able to identify this location both on the image as what to be rectified or geometrically corrected, as well as some base map or base image that we are extracting the map coordinates from. So we're going to be obtaining two distinct sets of coordinates associated with each ground control point. We're going to have image coordinates specified in terms of the row I and column J location of that particular point. So those would be coordinates that we extract out from our uncorrected or ungeometrically corrected image. And we would also be extracting out map coordinates. So, the XY coordinates in units of, say, feet, if we have a base map that is in a state plane coordinate system, or in units of meters if we have a base map or base image that is in a UTM or Universal Transverse Mercator projection coordinate system. So we have these paired coordinates, ij and xy, from many ground control points. For example, just as a rough rule of thumb, a heuristic, it could be 20 ground control points. It could be many more, or somewhat less. It really just depends on the accuracy requirements, the nature of the features that are captured within a remotely sensed image that are amenable to being or serving as ground control points. But anyway, we have some number of ground control points. And they can be modeled, these paired coordinates, in order to derive geometric transformation coefficients. And those coefficients then may be used to geometrically rectify or correct a remotely sensed image into some standard datum and map projection. There's actually a variety of data sources that can be exploited for the extraction of ground control point map coordinate information in order to perform what's referred to as image to map rectification. And by the way, I'll describe what that is, what that procedure is here shortly. But there's a variety of sources from which we can extract GCP map information, and that includes hard copy planimetric maps. That's a very logical, straightforward source. An example would be a U.S. Geological Survey 7.5 minute 1 to 24,000 scale topographic map. And I mention that scale just because it's quite detailed, and so we can extract out a ground control point that would meet accuracy requirements for a variety of mapping purposes. If it doesn't, then one could potentially use a hard copy paper map that is larger scale, that is more detailed, and hence the map coordinates that one extracts out from the map could potentially even be more accurate. But anyway, with this type of data set, a hard copy map source, the GCP map coordinates would then be extracted just using a ruler measurements or a coordinate digitizer. We could also utilize digital planimetric maps. So a planimetric map that has been digitized, the U.S. Geological Survey 7.5 minute topographic map series, again, would be an example of that. So it's basically just a digitized and georeferenced version of the hard copy paper map that I mentioned above. These are sometimes referred to as DRGs, or digital raster graphics. And in this case, we have GCP map coordinates just being extracted directly from the digital map on the screen. So as you move your cursor of the screen, you can extract out the map coordinates. Again, assuming that it is a geo-referenced map product. And then another source would be digital orthophoto quads, and these are images that have been already rigorously geometrically corrected, such that it appears as if we are looking down at nadir for all the features within the image, and that does often serve as a very effective base map, and we see potentially even more detail of various types of features within a digital orthophoto than what we might see in say a hard copy or digital paper map, or, a digital version thereof, just because those other data sources that I talked about above there on the slide constitutes abstractions of reality. So we see more detail potentially with a digital orthophoto quad. So an example would be U.S. Geological Survey Digital Orthophoto Quarter Quadrangle, or DOQQ. So again, that can potentially be highly effectively utilized. And also we could actually go out in the field with a GPS/GNSS type of receiver instrument to obtain map coordinates of various objects in the field ourselves. And if we have a real-time kinetic receiver, or if we perform a differential correction on the data that we collect out in the field, we can potentially have very accurate coordinates. It is highly recommended, though, that just to know the area, the exact feature that you are collecting data for when you are out in the field, it's usually a good idea to have some sort of an image map maybe with you that you can mark GCP numbers on that particular image map, so then you can associate the GPS point number and the associated coordinates with the feature that you're marking on the map. Ideally, it should come out the same, but again, that's a good way of just making sure that you're collecting data for the proper feature. So it's a good sort of a sanity check to employ when you're collecting those data out in the field. And by the way, there are derived products that could also be serving as source data for ground control points. An example would be digital line graphs. So these are vector features that have been extracted from U.S. Geological Survey topo maps. And as the term implies, they're in digital form, and they're also vector data. So again, if you have road intersections or building footprints, etc., that have discrete, well-defined boundaries, having them already in a vector form could also potentially be an effective means by which one could extract map coordinates for GCPs. Next, I will discuss the major types of geometric rectification. Keep in mind that if we have commercial remote sensing image data, or even some free government remote sensing data, depending on the level of processing that has been performed, oftentimes a lot of the systematic or predictable types of geometric errors have already been removed. However, unless otherwise processed, unsystematic random errors may potentially remain in the image, making it be non-planimetric in nature, which again means that pixels within the image are not in their proper XY planimetric position. Now again, that statement says unless the image has already otherwise been processed. Sometimes one can specify and download, again from a free government source, image data that have been further processed to remove these unsystematic random errors, or one could potentially pay a little bit more money for a commercial remote sensing image that has also been further processed to remove some of these unsystematic errors. But anyway, if we were to remove these errors ourselves, a couple of geometric correction procedures that are often used by scientists for Earth resource remote sensing include image-to-map rectification as well as image-to-image registration. And as a general heuristic or rule of thumb, one would typically want to rectify remotely sensed imagery to some sort of a standard map projection. So for a lot of serious remote sensing scientific studies, one would often want to perform an image to map rectification. So we'll be focusing on that in the subsequent discussion. I'll first discuss image to map rectification, and this is simply the process by which image geometry is made to be planimetric. And keep in mind that if we want to make accurate area, distance, and direction measurements for various features and locations within a remotely sensed image, we really need to perform image to map rectification. Also keep in mind that this type of correction may not remove or really minimize all of the distortions that may be caused by topographic relief displacement within our remotely sensed image extent. In order to minimize those sorts of errors, one would typically need to perform an ortho correction, but I'm not really going to discuss that here. That's outside of the scope of our discussion. So keep in mind that image to map rectification normally is going to involve selecting GCP image pixel coordinates. So that's just the row and column coordinate locations for a ground control point in the unrectified image, with the map coordinate counterparts, again for the same GCP, but we're extracting the coordinates, the map coordinates from some sort of base map or georeferenced image base. And say, for example, if we're dealing with the UTM map projection coordinate system, we would be having those coordinates in units of meters northing and easting. Or if we're using some other type of map projection or coordinate system, we would be utilizing the appropriate map coordinates with those GCPs. This graphic summarizes the process that one would follow in order to select ground control points or GCPs for the purpose of image to map rectification. And what we see here are two figures. On the left hand side is a digital version of a U.S. Geological Survey 7.5 minute 1 to 24,000 topographic map that is centered on a portion of Charleston, South Carolina. And if you are familiar with that city, you can see the battery, this hardened seawall that's running around the peninsula there of that portion of the city. And also situated on this particular map are ground control points. We have one that's labeled 13, another labeled 14, another labeled 16. These are just GCPs that have been assigned a numerical label. GCP 15 and the other GCPs that lead up to this sequence of number labels that we see for these GCPs. They may lie outside of this particular map extent, or maybe they've been deleted. It doesn't really matter. These various GCP numbers are just labels that have been assigned to the ground control points. And you can see quite a bit of spatial detail on this map. You see street intersections, you see building footprints for some major buildings within the area. So there's a lot of potential ground control points with well-defined boundaries that we could potentially utilize with this map base here. And keep in mind that this is a digital version of a topographic map that has been georeferenced. So there are map coordinates that are associated with these ground control points. And in this case, it's in the UTM or Universal Transverse Mercator projection. And so we would have the GCPs in map units measured in units of meters easting, that's for the X dimension, and meters northing, that would be for the Y dimension. Okay, so we have map coordinates for those GCP locations. And on the right-hand image, that is our unrectified image, the image that we want to geometrically correct. But at this stage, it is not rectified yet. And this, by the way, is a Landsat Thematic Mapper Band 4 image. It's a spatial subset of the overall image. So just keep that in mind. The amount of spatial detail is quite a bit less than what we have with our map base over on the left-hand side. So situating the ground control points may be quite a bit more of a challenge if we have a spatial resolution of this nature, which, by the way, is 30 meter pixels, what we have here. So the point is that when you are situating the ground control points, you're really going to want to zoom way in both on your map base image as well as your image to be rectified, your unrectified image. And note, you see the same ground control points on the right-hand side as what we see on the left-hand side. With the same numerical labels there. So that constitutes the image coordinate pair that we would match up with the corresponding map coordinates for the ground control points with the same labels that we see over on the left-hand side that are overlain on our map base. So when we're actually situating these, you would want to zoom way in on each one of these windows, and often in your digital image processing system, you'd have these up side by side so you could look at them back and forth to see the spatial correspondences between where the ground control point on our base map is versus that is georeferenced versus where those ground control points are on our unrectified image. And so in order to as accurately and precisely locate those ground control points at the sub-pixel at a floating point level within our unrectified image, we're going to want to zoom way in on those particular pixel locations, to the extent such that we would maybe only see that single pixel or maybe a handful of surrounding pixels within our unrectified image. And often you'd probably want to zoom in and zoom out at various scales or levels of visualization in order to properly and most accurately situate those ground control points, especially within the unrectified image in this case. But again, that would go both for your georeferenced image base as well as the unrectified image. Here I will just briefly discuss the image-to-image registration process. And what that is the translation and rotation alignment process by which two images of like geometry of the same geographical area are positioned coincident with respect to one another so that corresponding elements of the same ground area appear in the same place on registered images. So essentially we're going through the same process that we undergo with image to map rectification, but we simply use this process when it's not necessary in order to have each pixel assigned to a unique XY coordinate on some map projection. So an example of where we might use this is, if we just want to make a rough cursory initial approximate examination of whether or not maybe there's change between two images on different dates, we may just register one image so it matches the geometry of the other. We could perform image-to-image registration in order to perform that quick, rough type of a process. Now, I mentioned on the prior slide that the same general principles and procedures are going to be used in both image-to-map rectification as well as image-to-image registration. But there is a difference, and the difference is that with image-to-map rectification, the reference is going to be a map that is in a standard map projection, whereas with image-to-image registration, the reference is going to be another image. And that image, again, does not necessarily need to be rectified or georeferenced with map coordinates associated with it. And if we utilize a rectified image as the reference base, rather than, say, a traditional map source, any image that we register to it is going to inherit the geometric errors that exist within that particular reference image. So that's something important to keep in mind, and that's why most remote sensing research is going to be utilizing image data that have been rectified to some sort of map base, again with map coordinates that are associated with it. However, there could be instances where, for example, if we're performing a rigorous change detection between two or more dates, it might be useful to select what is referred to as a hybrid approach that involves both image-to-map rectification as well as image-to-image registration. And this is an illustration of the image-to-image hybrid rectification method that I was mentioning in the previous slide. On the left-hand side, we have a previously rectified Landsat TM Band 4 And on the right hand side, we have the unrectified image that we are interested in registering to the other image. And that base image, that other image, is a rectified image from another date. So we have a 5-year difference between these two images. So on the left, that image was acquired in 1982. On the right hand side, the unrectified image is an image that was acquired in 1987. So if the purpose is to perform, say, a change detection between these two images, it may be very important, and it would be very important to have the pixels, the exact pixels for corresponding locations with between these two images to be very accurately and precisely co-registered with one another. It could be utilitarian to have a rectified Landsat image as a base or a reference for the map coordinates as part of the geometric rectification process. And so you have ground control point pairs where you have the map coordinates from the rectified image on the left, and you have the image or row and column coordinates from the unrectified Landsat image there on the right. And so that's all what we really mean by performing an image-to-image hybrid rectification. So let's review the geometric correction process that we've discussed up to this point. We're going to need to determine whether or not we want to perform an image-to-map rectification or an image-to-image registration or a hybrid approach that utilizes aspects of each of those processes. And we're also going to want to establish a network of ground control points derived from some source, right? So we're going to have coordinates, one set of coordinates from our reference map, map base, if we are performing an image to map rectification, and we're also going to be extracting out image coordinates, row and column coordinates from our unrectified map. We want to make sure that we have as really many ground control points as we could accurately locate, and we're also going to want a good distribution of those ground control points to where they are fairly evenly distributed across the various quadrants of our data sets. Okay. And then once we have that established, we're going to have two basic operations then that we need to perform in order to geometrically rectify our remote sensing image to some map coordinate system. And again, we're going to focus here on the image to map rectification logic here. And the two processes are as follows. We're going to need to perform a spatial interpolation as well as an intensity interpolation. Now we need to identify the geometric relationship between our input pixel coordinates, so our column and row coordinates, and we refer to that here as x prime, y prime, and the associated map coordinates for that same point location, and we refer to that just as xy, right? So spatial interpolation involves a number of GCP pairs that are used to establish the nature of what that geometric coordinate transformation is. And we must apply that in order to rectify or fill every pixel in our output image, xy, with a value from a pixel in our unrectified input image, x prime, y prime. In addition to determining where our output pixels are going to be located, we also need to determine what the brightness values associated with those pixels are going to be in our rectified image. And there is not a direct one-to-one relationship between the movement of our input pixel values to the output pixel locations. We may have, again, pixels that drop out or disappear basically when we go from our input to our output image. And so we need to figure out what that process is by which we are going to assign our brightness values to our output pixel locations. Keep in mind that a pixel in a rectified output image often is going to require a value from an input pixel grid that does not fall neatly onto a row and column coordinate. Thus, there has to be some sort of a mechanism for determining the brightness value to be assigned to an output rectified pixel. And that particular process is referred to as intensity interpolation. When we perform image to map rectification, we are going to be utilizing polynomial equations that are fit to ground control point data that utilize least squares criteria in order to model the corrections directly in the image domain without explicitly identifying the source of the distortion. So, if we have these roll, pitch, and yaw effects or changes in altitude, whatever the exact nature of those sources of distortion, those geometric distortions are, we don't really need to identify and understand all of those sources explicitly when we are utilizing this ground control point slash polynomial equation-based geometric rectification approach, which is a strength of the approach. And depending on the nature of the image distortion, the number of ground control points that we're utilizing, and the degree of the topographic relief displacement that we see within our particular study area, higher order polynomial equations might be required in order to geometrically correct the data. So some experimentation and evaluation of the accuracy of various geometric rectifications would be in order to determine what order of polynomial equation would be best suited for a particular rectification task. And keep in mind that the order of the rectification is simply the highest exponent that is used in the polynomial equation. To better understand the different orders of polynomials that could potentially be used for geometric correction, let's consider this hypothetical example here. So here we're illustrating the concept of how different ordered transformations could fit a hypothetical surface that we illustrate here in cross section. So in the upper left-hand figure, we have the original observations. Okay, so we directly observe these data points, and in the upper right-hand figure is a first-order linear transformation that fits a plane to the data. All right, so this is what we would refer to as a first-order or an affine transformation, first-order polynomial. There is some deviation between this plane that we're fitting to the data and some of those data points that can be quite significant. In the lower left-hand corner, we have a quadratic equation, or what we refer to as a second order polynomial fit. And so you see that we have a better fit of that particular model to our original observation values. And the other example in the lower right-hand corner of this figure is a third order cubic fit, or a third order polynomial equation that we use. And we see that we have an even better or even closer fit to our original observations. Now, a question that you should ask yourself then is whether it is always going to be better to utilize a higher order polynomial, a third order or an even higher polynomial, such that we have a progressively better fit to our original observation points. In order to answer that question, you need to think about what utilizing a very high order polynomial would be assuming. And it would be assuming that, well, you have a large number of ground control points, and that those ground control points are accurately located, and that you also have a good distribution of ground control points. And the reason for this is that, well, if you have some ground control points that have not been located very accurately, and if you're very closely fitting your polynomial to those original observation points, that's going to induce or introduce a lot of error potentially into your rectification model. And if you also have areas of your image that do not have many or any ground control points, you're going to, have a significant blow up in the amount of error in those particular quadrants of the image. And we will see a higher magnitude of those geometric rectification errors in our output rectified image if we utilize a higher order polynomial in that case. Again, if we have significant areas where we don't have ground control points. So you need to select the order of your polynomial accordingly, considering the number, distribution, and level of accuracy of your ground control points. assuming that those characteristics of our GCPs are good and in good order. They're accurate, we have a good distribution, a good number of those GCPs. Then if we do have, let's say, aircraft data that has undergone maybe some pretty significant turbulence and wind effects, etc., then we may want to then utilize, though, a higher order polynomial in order to have a more accurate rectification. So the answer to that question in terms of whether or not a higher order polynomial is always going to be better, well, it's not always going to be better, and sometimes it is, sometimes it isn't. It would really depend on a given situation. So this is an example of an aircraft-based remotely sensed image that was geometrically rectified. This is a NASA Atlas near-infrared image with a 2-meter spatial resolution, and the image here was rectified utilizing a second-order polynomial in order to adjust for geometric distortions that were associated with the aircraft drifting off of course during the data collection, and the nature of the ground control points, the number, the accuracy, and the distribution of those GCPs supported the use in this case of a second order polynomial. Because there were some of these wind and turbulence related errors that we often see with aircraft, again, assuming our GCPs are adequate, it is often of utility to utilize a higher order polynomial equation, which is the case that we see here. And it's not uncommon for there to be curvature and wave sort of effects with geometrically corrected airborne imagery. It really just depends on the types of distortions that we might potentially see. In general, if we just have moderate distortions over a relatively small area, say maybe over a quarter of a Landsat scene, typically a first order 6-parameter, what we refer to as affine or linear transformation, is usually going to be sufficient in order to geometrically correct a remote sensing image to some map base. And that transformation is going to be able to model 6 kinds of distortion, and those distortions include translation, both in X and Y, scale changes, both in X and Y, skew, as well as rotation. And for image to map rectification, we utilize what is referred to as an output to input or inverse mapping logic, and we base that on these 2 equations here, one for x prime, the other y prime. So we have these equations where x and y, those are our positions in our output rectified map or image, and x prime and y prime, those are going to be the corresponding positions within our original input image. And our rectified output matrix is going to be comprised of our x and y, our column and row coordinates respectively, that we're going to be filling in a systematic manner. And this is simply an illustration of that spatial interpolation logic, where the goal is to fill a matrix in some standard map projection utilizing appropriate values from a non-planimetric image or unrectified image. So if we use the 6-coordinate transform coefficients that model the distortions that exist within our original image, we can use our output to input or inverse mapping logic in order to transfer or relocate the pixel values that we have within our original geometrically distorted image, those x prime, y prime locations, to a grid in our output rectified image, those xy locations. But before we actually apply the coefficients that will create our rectified output image, we determine how well those 6 coefficients derived from the least squares regression of our initial ground control points actually account for the geometric distortions that we have within our input image. And the method that we most commonly use in order to assess this is via the computation of the root mean square error for each ground control point. And we can separately compute the RMS error in the x dimension, the y dimension, or jointly x and y combined. And we can do this for each ground control point, and we can have a RMS error for the overall network of ground control points, or the total root mean square error across all GCPs. So here is the equation to compute the root mean square error. And so the RMS error is equal to what we see there. So we have x prime minus x orig, and we take that quantity squared plus x prime minus y original, that quantity squared, and we take the sum of that and then the square root of that quantity. So x orig and y orig, those are original row and column coordinates of our ground control point in the image, and the x prime, y prime values are computed are the estimated coordinates in the original image where we're going to be utilizing those 6 coefficients. And the closer those paired values are, the more accurate the algorithm and its coefficients are going to be in the geometric correction. And the square root of the squared deviations then represents a measure of accuracy of each one of those ground control points. What we do is we compute the RMS error for each and all of the ground control points. And in so doing, then it makes it possible then to determine which GCPs have the highest error, right? Because we can just look at the RMS E that is associated with each one of the ground control points, and we can also sum up all of the RMS errors. And as we either fudge or modify the locations of some of the ground control points in order to minimize its error, or as we delete some of those ground control points that cannot be well corrected, we can see how that changes the overall root mean square error of our rectification model. Now keep in mind that not all of the original ground control points that we have established are utilized in the computation of the final 6 parameter coefficients and constants that we use to rectify the input image. And the reason for this simply is that some of the ground control points that we have established initially have high spatial errors that are associated with them. They have high root mean square error values. So we either need to delete some of those values or modify their locations. And so we undergo then basically an iterative process to improve the root mean square error that's associated with each individual point, as well as we keep an eye on the total RMS error for the overall rectification model. So we go through this iterative process whereby we utilize all of our initial ground control points. Let's say we have 20 GCPs that we use to compute our initial set of 6 coefficients and constants. The root mean square error, our RMSE, associated with each of the initial ground control points then is going to be computed and summed to where we have a total RMSE for the overall rectification model available to us. Then we go in and we identify the individual ground control points that have contributed the greatest amount of error, and we determine which one of those are. And we can do this by, usually it's ideal to just order the list of ground control points by either the ascending or descending levels of RMS error. Doesn't really matter as long as they're ordered, so then we can easily identify the highest RMS error. And we would then either delete the highest error points, or we could go in and modify the location of those points to some degree in order to reduce the RMS error associated with them. But let's say we delete some that are bad, and that might leave only, say, 16 out of our original 20 ground control points, for example. So then a new set of coefficients would be computed utilizing, say, just the remaining 16 ground control points. And this process iterates. It continues until the RMSE reaches some user-specified threshold that would be appropriate for a given application. So it might be less than or equal to 1 pixel error in the X direction and the same in the Y direction. Often, rather than maybe less than 1 pixel RMS error, we may want to have less than half a pixel root mean square error. So if we have a 30-meter Landsat pixel, we may say that our acceptable level of overall root mean square error for a rectification model is only 15-meter root mean square error, or less than 15 meter. Right? And that is often the goal, to have less than half a pixel RMSE. So the goal would be to remove or modify the ground control points that introduce the most error into the multiple regression coefficient computation. And when we reach that acceptable threshold, the final coefficients and constants then would be utilized to actually rectify our input image to the output image in some standard map projection. And this table just summarizes the iterative process of improving the total root mean square error of our rectification model, whereby we have a listing of all of our ground control points in a table with a ground control point, a sequential ground control point number that has been assigned to all the GCPs, and that's listed over in the left-hand column of this table. You also see we have map coordinates in terms of the easting and the northing map coordinates for the X and Y dimensions respectively, and we also have the X and Y pixel coordinates or the image coordinates for that GCP as well. So we have paired map and image coordinates for each ground control point. And if we order by root mean square error all of our ground control points, then we can go in and basically just delete the highest root mean square error point. And after we do that, hopefully we should improve the total root mean square error associated with a rectification model. So if we start out, say for example, with all the ground control points that are utilized in the computation of the total root mean square error. So let's say we start out with 20 ground control points. We delete point 20 because let's say that has the highest RMS error that is associated with it. After we do that, then we would bring the RMS error down from 11 meters. Let's say it's meters if it's in UTM coordinates. So from 11 meters down to 8 meters. And we can progressively and iteratively go through this process to where we ultimately wind up with a much lower root mean square error if we, in the next step, delete the next highest root mean square error. The next step, we delete the next highest root mean square error, and so on. Now, we don't always necessarily have to delete higher root mean square error points. We could potentially go in and zoom in, usually at the subpixel scale, and move at the subpixel level, kind of fudge around the spatial location of that ground control point, since if it has a high RMS error, that might suggest that it has been somewhat inaccurately spatially located. However, if you do modify the spatial location of that point, you do not want to move it significantly off of where you know that it should be or think that it should be, just because that would tell us then that there's probably something wrong, not only with that point, but also potentially some of the other points that are used in our rectification model. So that would suggest either that we need to delete that point or modify not only that point, but some other points in the overall network of GCPs. So just be aware of and careful about that. You can make some minor modifications, but if those minor modifications are not sufficient, if you have to move it significantly off of where you think it should be, you might be better off just deleting that point. And again, it's not uncommon to have to delete some subset of the points in order to have a set of GCPs that have been accurately located, and you have good confidence in those points. And whereby the total root mean square error, again, meets that acceptable threshold of accuracy. Regarding the intensity interpolation, here we are extracting a brightness value, or BV, from an X prime, Y prime location in our original ungeometrically rectified input image and its relocation to an appropriate XY coordinate that exists within our rectified output image. So the pixel filling logic that we utilize is going to yield an output image on a line by line, column by column basis. And typically our X prime, Y prime coordinates that we're going to be sampling in our input image are going to be floating point numbers. At the subpixel level, they're not going to be integers. So for example, there's an example in the figure there where we have pixel 5,4, that's in the XY, that's our XY coordinates in our output image. That's going to be filled with a value from coordinates 2.4 and 2.7 X prime, Y prime in our original input image. So in this scenario, then, there's several methods of brightness value intensity interpolations that we could potentially apply, and that includes the nearest neighbor method, bilinear interpolation, or cubic convolution. And all of these methods are referred to as resampling methods. So we have nearest neighbor resampling, bilinear interpolation, and cubic convolution resamplings, respectively. And this is an illustration of one of the resampling methods that I mentioned, along with the corresponding figure that I was referencing in the prior slide. Specifically, this is an example of nearest neighbor resampling, and this is where we're taking the brightness value that is going to be closest spatially to our predicted x prime, y prime coordinate, and we assign that brightness value to the output xy coordinate. So we're not changing any of our original data values. We're not necessarily utilizing all of them from our original input image. Again, some pixel locations may disappear from our original input image to our output rectified image. However, since we're just utilizing the closest pixel, and the brightness value associated with it, we're not changing any of our original input brightness values as part of this nearest neighbor resampling process. Regarding bilinear interpolation, we're basically going to be utilizing the brightness values of the four nearest surrounding pixel locations in order to compute a new weighted output brightness value. So we're assigning output pixel values by interpolating BVs in the two orthogonal directions within our input image. So we're fitting a plane to four pixel values that are going to be nearest to our desired position, and then we're going to be computing our new brightness value based on the weighted distances to those points. So for example, the distances from our requested position at 2.4 and 2.7, that coordinate position in our input image, to the closest four input pixel coordinates that are listed there. We're going to compute that, and the closer a pixel is to the desired XY location, the more weight that it's actually going to have in the final computation of that weighted average that we're computing. So there's the equation there for bilinear interpolation. So that sub WT subscript just denotes that we're computing a weighted brightness value, weighted average. And this is an illustration of the bilinear interpolation process utilizing those four surrounding brightness values. And with cubic convolution, we're basically taking the bilinear interpolation process a step further, whereby instead of just the four surrounding pixel locations, we're taking into account a neighborhood of 16 pixels that surround the location of our desired x prime, y prime pixel location in order to determine the value of our output pixel or brightness value. So we see the equation there for cubic convolution, whereby we're computing this weighted brightness value utilizing the 16 surrounding data point values. Now, something to keep in mind is that the net effect of cubic convolution, say in contrast to bilinear interpolation, is that since we are utilizing a larger neighborhood of surrounding pixels with cubic convolution, we're going to have a greater smoothing effect, greater averaging of our brightness values, and so we're going to have a visually pleasing output rectified image, right? Because we're going to have this smooth gradation of brightness values, and so we'll have a greater smoothing effect with cubic convolution compared to what we would see with bilinear interpolation. However, with bilinear interpolation, it still can be visually pleasing, may not be quite as smooth, and gradually undulating brightness values is what we would see with cubic convolution, but we wouldn't be as significantly changing the data values from our input image. However, if we want to perform quantitative biophysical remote sensing, for example, whereby we're trying to estimate parameter values of interest for some type of phenomenon, let's say for vegetation, we're interested in estimating the amount of healthy green biomass that exists within a given pixel, or we may be interested in estimating leaf area index, or some other sort of biophysical parameter. If that is of interest, then we're usually going to want to utilize nearest neighbor resampling, because we're not going to be changing any of the original input data values in that case. So for a lot of most scientific research purposes, even though it may not be as visually pleasing and we may have some sort of kind of a blocky jagged visual effect that we see after the nearest neighbor resampling process, that's still usually going to be a preferred method because we're not going to be changing the actual input data values when we are performing that type of resampling. So that's something to keep in mind. And when you get the data from the data provider, it's very important to look at the metadata to see if it has already been geometrically rectified in some manner, what type of image intensity interpolation or resampling has been utilized. Because if they've already applied cubic convolution and you want to utilize those data for some biophysical estimation purpose, then you really probably should go back to the original data, the unrectified data, and perform that rectification process yourself using nearest neighbor resampling. So that's something to be aware of and pay attention to. And this graphic is an illustration of the cubic convolution intensity interpolation process, whereby we're utilizing the 16 surrounding neighbors in the computation of our new brightness value. And with that, that concludes what I wanted to discuss with respect to the geometric image rectification process.